Okay, it's my great pleasure to introduce Catuscia Palamidessi, who's going to give an invited lecture. Catuscia is Director of Research at INRIA. She's very well known for her work on foundations of secure information flow, differential privacy, other forms of privacy, fairness in machine learning, and related topics. She's also worked extensively in semantics and concurrency. A paper on comparing expressiveness of synchronous and asynchronous calculi is one of the jewels of concurrency. A couple of years ago, she was awarded the very prestigious Grand Prix of the Academy des Sciences. Her lecture today is Information Structures for Privacy and Fairness. So that's
Thanks a lot, Samson. And there is an echo.
Keep on, so you can get yourself on the left.
It's muted.
Oh, don't you the sound?
Yeah. Okay. Yeah, thank you. So thanks a lot for the introduction, Samson, and thanks to the organizer for inviting me here. It's a real pleasure to be back at MFPS and see so many of my old friends actually in Singapore for a long time. So I'm going to speak about both information structures, but mostly is methods from information theory and for statistics for privacy and fairness. This is the plan of the talk. We'll first introduce differential privacy, which is the most popular approach to privacy. And then I present a variant, or say a generalization of differential privacy that we call deep privacy. And then we speak a bit of a few mechanisms that come from, in particular, one mechanism that comes from information theory, which is the Blatter motor obfuscation mechanism. And then I will speak about the trade-off between privacy and utility, and for this purpose, I will introduce a method from statistics that we call interactive Bayesian data. And I wish you a funny thing that we have it's a sort of remark. It's nothing very deep, but it's interesting. It's an interesting duality between these two methods, the iterative Bayesian update and the Blatter model. And then in the last part of the talk, I will speak about fairness in machine learning, and I will show a solution to one of the problems that raise fairness, which we have solved by using the iterative Bayesian update. So let me start with the privacy. So everybody knows that there is a problem that with the machine learning and the big data, there is a lot of concern about privacy. I mean, the problem of privacy has always been there, of course, but in the modern time is magnified by orders of magnitude. And the problem is that big data will not go away because they're too useful. So we have to find a way to make sure that we enjoy the utility of data and machine learning while preventing bad guys to access data and to sensitive data, which could harm the data owner in various ways. So the problem of utility is indeed the main problem with privacy, because of course we want to try to protect privacy while preserving as much as possible the utility of the data. And in fact, the holy grail of the research in privacy is to find the so-called optimal mechanisms, namely the mechanisms that maximize utility for certain degree of privacy, or viceversa, privacy with a certain degree of utility. And there are various notions of utility, but in this talk I will mainly focus on two of them, which are the so-called the quality of service, which is a notion of utility from the point of view of the data owner, and the utility, the statistical utility, which is from the point of view of a data consumer. So let me start by introducing differential privacy. I guess most of you know already what it is, but let me recall it. So differential privacy was introduced about 20 years ago by Cynthia Dort and their colleagues, and this still nowadays the most successful framework for privacy. It has been really a very, very booming field with a lot of publications, a lot of variants, a lot of research, a lot of people that got interested, a lot of intersection with other fields too, in particular machine learning. So the differential privacy essentially, differently from previous approaches to privacy, is based on the idea that we shouldn't access the microdata, but we should collect the data in a sort of trusted server. And then the interface, the server has an interface with the good guys that want to analyze the data. And for every query that the good guys might ask from the data, there is a there has to be designed the mechanism that the obfuscation mechanism that is particularly tailored for that query, and that well, obfuscates the data and tries to do to preserve the utility as much as possible. From this point, for this model, which is also called the central model of differential privacy nowadays, the main notion of utility is statistical utility. So, how after the obfuscation, how good is the statistics that I can make? I should also clarify that the obfuscation is not done on the data, but directly on the result of the query. So the server, or the guy that controls the interface, which is called the data curator, computes the result of the query on the true data, and then sends an obfuscated answer. Neither the good guys nor the bad guys have direct access to the server, to the data contained in the server, in principle. Formally, differential privacy is defined like this. Oh, do we have a pointer, by the way? No. It's okay.
Oh.
Yes. Yeah, should we do it there? I don't know what to do.
Yeah. It's giving me anxiety. Thanks. Yeah.
So it is called the differential privacy because it protects the most the single unit of information, which is a single data record. So essentially, in differential privacy, we have this notion of adjacency between databases, which we say two databases are adjacent if they differ for only one record. And now, if X and X prime are adjacent, we require for a mechanism K to be differentially private that every answer that you get that this mechanism produces with a certain probability P can be produced almost with the same probability, the same answer, with both an X and an X prime. Okay, so the answer that I get from X prime have the same probability to be produced than the answer that I get from X. And the idea is that a malicious entity that has access to the answer of the mechanism cannot distinguish whether the record, whether the database is X or X prime. So principal cannot say whether the record is in the data set. The properties that have made the success of differential privacy are essentially these two. First of all, it is compositional, which means that if you combine the information that you get from queries protected with the differential privacy mechanism, the result is still differentially private, although the parameter, although the degree of privacy decreases a bit. The degree of privacy is established by this epsilon here that is the ratio expresses here the power of epsilon expresses the ratio, the maximum ratio of these two probabilities. So when you combine two mechanisms, essentially the epsilon sum up. The other important property is that it's independent from side knowledge. In other words, there is nothing in the formula that speaks about the knowledge of the attacker, which is a good property, at least in principle, because it means that I don't have to design different mechanisms depending on what kind of attacker I get. Right? But if a mechanism is differentially private for an attacker, it's differentially private for independently from the knowledge they have. And so this was mainly, the central model was there for a very long time, about 10 years, but then recently people have started worrying about what happens if the attacker can get inside the server. And this is something that has happened in reality, right? Cambridge Analytica, where the server was not very friendly, say, or even if the server is honest, but maybe just incompetent and not to be able to prevent the privacy security breaches, right? So it could be that data are at risk. So to prevent that, people have started looking at the so-called local model of differential privacy, and this has been very successful, especially because the big tech companies have supported this line of research, and they have their own implemented their own mechanisms for local differential privacy. So the architecture of local differential privacy is quite different because in this case, the data are obfuscated directly at the source. So the trust boundary is here. Each data owner, before letting this data to be collected, obfuscates the data on this side, maybe with different degree of privacy, different mechanism. And so what gets collected is already obfuscated data. So even if the malicious entity has access to the collected data set, only gets the obfuscated information. And in this case, there are two notions of utility that are used that are interesting. Statistical utility still, I mean, the kind of precision of the analysis that we can make on the obfuscated data, but also the quality of service, because in general, if you release your data is to get, hopefully, to get some service, get something in exchange, right? Typically is a service. And of course, if you send obfuscated the data to the service provider, probably you're not going to get the same quality of service. So in this case, there are these two kind of utilities that we take into account. Now, to explain differential, so the definition of local differential privacy is very similar to the one we have seen before, except that now X and X prime are not data sets, but arbitrary data points. And there is no notion, of course, of adjacency because they're just two different data points. To explain how this works, so I like to make to recall the so-called randomized response mechanism that was invented actually a long time ago, long before differential privacy was even conceived. The idea is, so it was invented by Warner. He was worried about collecting, making polls, making surveys. And he was worried that if you ask an embarrassing question, people may not answer truthfully. So he devised this mechanism, which consists of, so suppose that the answer to the query, to the question is either yes or no, is binary. Then the person who's asked the query tosses a coin, and depending on the result of the coin, it says the truth, or he flips again the coin, tosses again the coin, and he answers whatever the coin says. So, for instance, yes, if it's head, and no, if it's tail. So, if the coin is fair, we can see that the probability to answer truthfully is 3 over 4. And of course, the probability of being the wrong answer, the false answer is 1 over 4. Which means, if we look at the formula, means that this is a differentially private mechanism with epsilon equal to log of the ratio between these two, which is 3. So log of 3. Is it clear? And this mechanism is actually, although very simple, has been very successful. It is, for instance, the core of the system implemented by Google, which is Rapport. Of course, if it was only binary, that is not very useful, but it can be extended to arbitrary size, arbitrary domain size. And it becomes what I call the flat mechanism, or more commonly is called the KRR, for KA, randomized response. And the and the function and the probability function is this one. So you answer truthfully with the probability C times E to the power of epsilon, or answers with the probability C any other element in the domains. So for all the answers that are not the true answer are given with the same probability. And C is this normalization factor that depends on the size of K of the domain. And this mechanism, well, local differential privacy in general is the same with the properties as differential privacy, and is compositional and independent from the sign of knowledge of the adversary. Now, I will speak also about the privacy, which is nowadays called the metric differential privacy. It's a generalization that we did for generalization of both local differential privacy and central model differential privacy. Essentially, the formula is the same, except that now X and X prime can be anything, any element or any elements of a metric space. And the formula is almost the same, except that we, in the exponent of the factor between the two probabilities, so we also multiply epsilon by the distance between the two data points that we want to make indistinguishable. So this is a generalization of both the differential privacy and local differential privacy, because you can obtain differential privacy by instantiating, by considering a domain consisting of data sets. So X and X prime would be data sets, and D would be the Hamming distance between data sets, which is the number of records of which two data sets differ. Or you can get a local differential privacy by imposing that V is the discrete distances. The distance is 0 if the two elements are the same, or 1 if the elements are different. And again, you get the same good properties of differential privacy. So this compositional is independent from the private distributed from the knowledge of the attacker. And it can be applied like local differential privacy at the owner side. And in fact, the main uses that have been done of this proposal is for the local model. Essentially, the difference between local differential privacy and metric privacy is that, as I said before, the local differential privacy, in particular the KRR mechanisms, distributes the obfuscation uniformly, distributes the noise uniformly. So every point in the domain, if it is not the true answer, every other answer is given with the same probability. So one point can be, if you are in a metric space, one point can be sent very far away from the true point. Whereas metric privacy tends to concentrate the probability in points that are nearby the true point. So depending on the notion of privacy that you want to achieve, so if, in particular, if you are just worried about making your secret indistinguishable from all the nearby secret points, and if the notion of utility is the proximity to the true point, then the privacy offers a much better trade-off, utility privacy trade-off than local differential privacy, than the KRR mechanism in particular. And a lot of applications for this come from the domain of location data. So there the metric privacy takes the name of general distinguishability. Essentially, location data points of the locations, and the notion of distance between them, general distinguishability, is the Euclidean distance. To simplify, I mean, it should be the distance on Earth, but it's much easier to make calculation using the Euclidean distance. So to get an idea is of how you can use this is, for instance, if you are in Paris and you want to find the point of interest near you, for instance, restaurants, this mechanism will report a location which is probably not yours, but not very far away. And so the service provider will report to you a set of restaurants near the point given him, but we are still close to you. So it gives a good protection, for instance, if you told your boss that you are from the Paris, but in fact you are in someplace else in Paris. But of course, it doesn't protect you from being revealing that you are in Paris instead of Oxford, for instance. Right? So it depends on the notion that you want. Typical metric privacy mechanisms are the Laplace, the planar Laplace for general distinguishability, which is well, like Laplace, but isotropic of the plane, and the geometric, which is just a discrete version of the Laplace, and the discrete version. So in other words, it's a mechanism that reports the points or reports points with decreasing, exponentially decreasing probability for the location where you are. Now, this was quite successful, but there is a limitation, namely, it does not protect from isolation. It does not protect isolated locations. So, for instance, if you are in an island surrounded by water, a lot of water, then the Laplace will probably report a point in the water near the island, but an attacker will know that you are in the island because it's likely that you are, say, using your iPhone when you are in the water. So this is this kind of vulnerability. And to try to amend this, we have looked at the information theory, and in particular rate distortion theory, where we have found an interesting result to that remote. Is in fact one of the algorithms that belong to the same class of the algorithm that computes the optimal capacity. But in this case, the problem is, sorry, the optimal encoding of the capacity of the channel. But in this case, the encoding, the problem to be solved is the following. Given a certain prior distribution, we want to find the optimal stochastic, the optimal information theoretic channel, so stochastic matrix like the one you have seen for the randomized response, which optimizes the trade-off between mutual information between the input and the output, and what they call a distortion, which is essentially the expected distance of the output from the input. So in other words, we want to find the point of the Pareto optimality between mutual information and distortion. Of course, there is a trade-off between mutual information and distortion, because the more close you are, the more information you give. So, or vice versa. So the idea is that Pareto optimality gives all the points on the frontier of the Pareto slope are those points which, for a given distortion, give the minimum mutual information, or vice versa, for a certain mutual information, give the minimum distortion. So we use this for defining, the way it is computed, this optimal channel, is via an iterative process, which essentially tries to to define a channel that reports points which are where there is already an accumulation of points in the original distribution, in the true distribution. So it's an iterative, mutually iterative process between defining the channel, refining the channel, and refining the output of the channel. I will speak a bit more about that later. So if we take the limit of this iteration, we get for the channel, you get a point on the slope. And the nice property of this mechanism is that well, first of all, it optimizes the trade-off between mutual information and distortion. The mutual information can also be considered the notion of privacy. So how much privacy you get about the input when you know the output? How much how much information you know about the input when you see the output, right? Distortion also can be considered a measure of utility, especially quality of service, because usually if you report the point it's too far away from the real point where you are, you don't get a good service. And on top of that, he solves it is a good measure for isolated points. And here, this graph gives an idea of the difference between the Blatter remoto and the Laplace. For instance, if this is the original distribution, so there is a lot of population here and nothing here, and you are in this island here, if you use the Laplace, you will report a point around the island according to this distribution. This is just the difference distribution that you get when you change the epsilon parameter. If you use the Blatter remoto, and if the epsilon is small enough, then you will probably report a point where all the rest of the population is. Whereas, well, as epsilon increases, you will tend to be more and more close to the island. Now, so I have already given an idea that the Blatter remoto, sorry, the metric differential privacy has a better utility privacy trade-off than local differential privacy, especially if you consider the quality of service. But what about the statistical utility? So, I forgot to say, by the way, that the Blatter remoto also satisfies metric privacy, and there is a relation between the parameters that you find with the Blatter remoto and the epsilon, which is epsilon just twice as much the parameter of Blatter remoto. So, okay, so what does it mean to what does it mean a statistical utility? Well, essentially the utility of how good are the analysis that you can make on the obfuscated data. I will focus on one particular notion, which is the estimation of the original distribution, which I would say is the most basic notion of the body of statistical utility, because if you know the original distribution, you can, I mean, if you have a good approximation of the original distribution, then you can make the analysis directly there. So the idea is that you have your privacy mechanism, you have an original distribution pi. The population, the data are sampled by from this original distribution. And then each data point is transformed according to the privacy mechanism, the data point. So at the end, what is available for a data analyst is the set of obfuscated data points, and this gives an empirical distribution, which is of course different from the original distribution pi in general, because of the noise of the privacy mechanism that is used. Now, having knowledge of the empirical distribution and the privacy mechanism, we want to find an estimation method that allows to recover a good approximation of the original distribution. So we are interested in minimizing the distance between pi and p, where p is the result of the estimation method. And to give an idea of how a possible mechanism works, let us mention the matrix inversion method, that is the simplest estimation mechanism that was proposed by Kairos in the context of differential privacy, but it was already known before. So the idea is that if the matrix that gives you the probability of the output given the input is invertible, then to find a good approximation, well, to find an approximation of the original distribution, you just multiply the output, the empirical distribution in output, by the inverse of the matrix. And if, well, let's consider, for instance, how this works in the case of a randomized response. So you remember you have this matrix here for randomized response. Now suppose that you make your survey and you get, you ask, for instance, are you bored by my lecture? And you get 60% of answer yes and 40% of answer no. So are you happy with this answer? Of course not, right? Because reality is much worse. In fact, if you apply, I mean, if you make some calculation, namely you compute the system of equation that comes from this coefficient, the answer that you get, and the input probability considered as an unknown variable, the input distribution considered as an unknown variable, you find out that the solution to this system is 70% yes and 30% no. So this is how the matrix inversion works, but well, there are some problems. First of all, C must be invertible, otherwise you cannot apply the inverse. But also, you don't always get a distribution when you apply this method. For instance, if you start with an empirical distribution that is 80% yes and 20% no, you solve the system and find out that the people that are bored by my lecture are 110%. So even the people outside. And the people who are not bored are minus 10%. Strange. And why is that? Well, it's not that the method is wrong, it's just that there is a lot of what the method, so this method assumes so that we get an empirical probability that is the ideal probability that we get by multiplying the matrix by the original distribution. But in fact, there is a lot of randomization, right? The noise is sampled from the distribution, so you don't know what you get. And to give a better idea of what is happening, let's look at this diagram. So you start from, when you apply the noise, you start from an original distribution pi, and ideally, you get the result of pi, the matrix multiplication of pi by C. Now, this, if a C is invertible, this is an injection, right? Because in fact, you can go back to the same pi by applying the inverse of C. However, you don't always get, in practice, you don't always get this when you apply the noisy mechanism. You could get a different, I mean, you usually get a different distribution, empirical distribution too. And so when you go back by applying C-1, you don't get pi, you get something different. You certainly don't get pi because, as I said before, it's injected, right? Even worse, it could happen. So this the application, the multiplication by C is a contraction on the space of distribution, right? So there are some distributions that are left out from the image, but you still can get them because of the randomization process. Because something the noise is a random process. So you could get a Q which does not really represent the result of any multiplication of any distribution by C. And so when you go back, you get a point which is out of the simplex. Now, what do you do at this point? So this is exactly what happened before, right? The example of 110%. So if you get something that is not a distribution, well, you can get the distribution by either normalizing or going to the closest point on the symmetries. And this is, in fact, what has been proposed in the literature, the matrix inversion method, as these two possible amendment, possible way to get through the distribution. And the matrix, this method works quite well if the mechanism is KRR, but it doesn't work on any other mechanism, in particular not in those for metric privacy. And I think it's because KRR is a sort of linear. It's a very simple matrix, in fact, it's a diagonal matrix, but the other, for instance, the geometric is a very different matrix, much more complicated. So for computing the best approximation, the best estimation of the original distribution, we have looked at methods from statistics, and we came out with the iterative Bayesian update. Actually, it's not our invention, and it was already in a paper by Agraval, but not in the context of differential privacy. So the iterative Bayesian update is based on the expectation maximization method, which is probably the most famous method in statistics, which has the property that it produces a maximum likelihood estimator of the true distribution. And if the matrix is invertible, then the maximum likelihood estimator is unique. And this has the nice property that the more data you insert in the mechanism, the more the estimation converges to the true distribution. This comes from the law of large numbers. But the expectation maximization method is very cool. So let me give some idea about it. Promise is just it's only a couple of pages of formulas, a couple of slides of formulas. So the EM method is based on the idea that we want to maximize the likelihood of. So remember, what we have at our disposal is the empirical distribution Q, and we know the mechanism C that has produced it, and we want to estimate pi. So we do this by maximizing the probability, trying to find the distribution R that maximizes the probability to get Q in output. So this, and we apply a log in front because it's easier to make calculation with the log. So this is what is called the likelihood. The maximum likelihood has this nice property, by the way, that if you find that the R that maximizes the likelihood, the log likelihood, this corresponds to the R that minimizes the distance, the Kullback-Leibler, sorry, not the distance, the Kullback-Leibler divergence between R and Q. And this is, oh no, sorry, it's between R and P, pi. Yes. And this is a nice property because, well, I'll speak about that later, but you know, the Kullback-Leibler divergence is a notion very much used in information theory because it has a lot of nice properties. It's not really a distance, but it has, well, it's a measure of the difference between R and Q in this case. And remember, this is not, should not be Q here, and this formula should be pi. It's essentially the cost that you have to pay if you think that your distribution is R, whereas the true distribution is pi. discrete and Q bar should be fast. So it is in a sense a notion of utility, right? From the statistical point of view, the statistical analysis point of view. Now, to compute this maximum likelihood, log likelihood, it's usually very difficult to do it directly. What the people do in general is to put to add in the calculation of some other latent variable, and which is different from case to case. In our case, this latent variable, we found that a convenient latent variable is the set of true points that have been sampled by the true distribution pi. And we define this formula here. I mean, it's the expectation maximization method that gives this methodology. And the nice thing, so Q essentially is the expected value of the log likelihood with respect to the input, the probability of X computed in some previous estimation of the prime probability. So this Q has a nice property that the log likelihood of R minus the log likelihood of R prime is always greater or equal than Q, and then this formula, which means that if we optimize, if we find out the maximum value of Q, I mean the R that maximizes Q here, that also maximizes the log likelihood with respect to the previous step. And I mean, not maximizing, but increases at least. So now, since we are in a compact space, and the log likelihood is a continuous function, this means that bounded by 1, of course, because it's, no, by 0, sorry, because it's the log of the probability. This means that eventually it will converge, this process. Now, in our case, the computation of the maximum value of the R that maximizes Q is given by this formula, which, if you think about it, as this core, essentially the bias theorem. That's why it's called the iterative bias update. And of course, now we have this transformation, which we call the T, that gives that converges no matter where you start from. Well, sorry, you have to start from a fully supported distribution, for instance, the uniform distribution. And so by applying this formula again and again, you will eventually converge to some P that is hopefully close to the true distribution. And it will be the expectation maximization method assures us that it will be, if the matrix is unique, is invertible, this tau has only one fixed point. This transformation has only one fixed point, and the large numbers will also ensure that as you get more data, the more this P will approximate the true distribution. Now, one nice thing about this P is that in all experiments we have done, it turns out that this T is a contraction with respect to various metrics, including the Euclidean metric, and also with respect to the Kullback-Leibniz divergence. So we conjecture that this is indeed the case, but we haven't been able to prove it to be a contraction for any of these metrics, Kullback-Leibniz for the matter. But well, this would be, if we can prove this conjecture, this would be very useful. First, because it would provide an alternative proof of convergence using the dynamic exponent theorem. This would work even if we take the case of the Kuba-Clavier divergence, because Kuba-Clavier has all the properties that make the fixed point theorem work. But okay, so not only that, but we would also, if we could compute the contraction parameter, which is usually something smaller than 1, just to be strictly smaller than 1, this will give us a formula. I mean, we could compute the contraction parameter with respect, which probably will depend from the obfuscation mechanism, so the matrix C. This would give us an idea of the convergence speed of the method. Anyway, in all our experiment, we have seen that this converges relatively in a matter of 10 iterations. It gives a very, very close approximation of the true distribution. I'm going to show quickly how. Okay. I'm going to show quickly how this works with this example of the Govalla dataset, which is a collection of location data. So this particular one is a distribution of location data in an area of San Francisco. This is the same representation, the same thing that I'm presenting in histogram. There are about 10,000 locations. So if we take this distribution and apply the Laplace mechanisms for method privacy, of course, this mechanism is a noisy mechanism, so it flattens the distribution quite a bit. And then by applying the expectation, the iterative Bayesian update, we can reconstruct the distribution, an approximation of the distribution. So what you see here, it's it's an animated GIF. So every photogram represents one iteration, the result of one iteration of the method. And yeah, as you can see, it converges. I have done here 300 iteration, but I'm going to stop it now. Stop it. If we use, on the contrary, the KRR mechanism, well, first of all, it becomes much more flat. Because, as I said before, the KRR can send any data point in any place in the domain, so no matter how distant they are. And if we apply now the matrix inversion of the iterative Bayesian update, we get a much worse result. And I'm afraid I don't have the time to speak about fairness. Well, I can say something very quickly, or maybe it's not here. Here are some experiments. Ah, yes, I want to mention the duality. Yes. So you remember the formula of the iterative Bayesian update, which is this one. And the Blattari method, well, I told that very quickly, but is this formula here. And now if you look carefully at that, the Blattari method takes an input pi and produces as a side result and produces the empirical distribution Q for the optimal mechanism, for the Blattari method mechanism, so for the optimal channel. The iterative Bayesian update does the other way around. It takes an input, the empirical distribution Q, and produces the optimal distribution P, namely the distribution that is as close as possible to pi. And if you look at the formula, they are exactly symmetric, right? Where there is pi in VA, there is Q in IP book, and where there is well, the rest is completely symmetric. So think of pi as think of p as an approximation of pi, and then you start. And we think that this is the reason why the black remoto work so well together, with very good utility privacy trade-off. And I'm sorry for the amount of time for fairness. Unless I can use 3 minutes.
Oh, yes, we should have some time. Questions, please.
Okay, then I stop it.
Very much. Questions?
It's weird to me that the pullback libraries are using metric don't have relation, but still you're first.
Sorry, the
divergence and the utility metric don't have a relation to each other, but still your method would use them at that direction. Did you also consider another distance of distribution? It's created with the original.
Oh, yeah, sure. In fact, the utility we measured, yeah, I didn't show the slide, but when the experiments where you see the Megovana data set, to measure the utility, the statistical utility, we use the versus time distance. And I think that's quite one of the most relevant metric for utility because, I mean, depends on the application, of course, but for instance, if you want to have a good idea of the distribution and the quality is even if you are not putting the mass on the right point, but if you put it in a point nearby, it's pretty good. Then the Kantorovich, sorry, the Sestein Kantorovich made the idea great.
Yeah.
I don't have a question, but a remark. What you are using for these computations backwards, there is an abstract construction called the Decker of a channel, which is the reversion, Bayesian inversion of a channel, which is what you seem to be using here. And this Decker of a channel, this gives rise to a certain update we call Jeffrey's update, which is also used in learning. And it forms the basis of the EM mechanism. So I think it is important. It might be useful to do that. One of the crucial properties of this Jeffrey's update is that it reduces KL by functions.
It does. Okay, so that's the use of the contraction I'm looking for.
Precise. Well, I don't know if that precisely is what you're looking for, but it's definitely in the same.
Please send me the link. It's very helpful. Thank you.
Well, I'm tempted to ask a sub question. Could that be related to this intriguing duality?
I don't. That's the same question I have. I'm keen to look into this more.
Yeah, it's intriguing because these two methods came from very different, very different purposes. Right? One was for computing a latent variable, the other was for computing a channel. I don't know. I think I didn't see this duality pointed out.
Very intriguing. Yeah. Other questions? Yeah.
Yeah, so in the case the C matrix is uninvertible, do you have any other options like workarounds, or we just can't apply it?
It's not invertible.
Yeah, the C.
If it's not invertible, then the problem is that you have infinitely many distribution and input that can give you the same output. And this is a problem because it will not converge even if you give a lot of data. You what happens? Well, you can apply the therapy based on data because that doesn't need the inverse, but you're not guaranteed to find the fixed point you find is not. So first of all, the fixed points are not unique, and so depending on where you start from, you will find a different fixed point, and that can be very far away, or maybe not very far away, but it's not going to converge to the true distribution.
Yes, if this method breaks down, but is there like workaround on the or you just the
It's impossible. It's I mean, think about that. In a very suppose that is the coin that you throw in the randomized response always give the answer always gives tail, and so you always flip the coin again and you answer whatever the coin says. So that gives you half an answer probability to say yes or no. And so what you collect is always 50% yes or 50% no. You have absolutely no idea what the 3% is.
Just maybe one more question for this one. So let's thank